Good afternoon and welcome to this session on machine learning in production, serverless and painless approaches. In the next 30 minutes and a bit more, I will walk you through some of the challenges that appear when you want to productionize machine learning models and some ways to do this as easy and painless as possible in the cloud. And I'll use a simple case study as an example to highlight and illustrate some of these points. But before we dive into the topic, I just quickly want to introduce myself. My name is Oliver Gindele, and I'm the Chief Innovation Officer at Datatonic. My background is originally in computational physics, and that brought me into data science and machine learning a few years ago when I joined Datatonic. In case you don't know Datatonic, we are a boutique consulting firm that specializes on delivering data solutions for a wide selection of a wide range of clients and industries. So it's predominantly data solutions on Google Cloud Platform for industries such as retail, media, or telco. But let's get straight to the difficult question. Why is moving machine learning models into production so hard? If you're not very familiar with machine learning overall, I want to actually take a step back to answer this question and illustrate a little bit the life cycle of a machine learning project. If you think of machine learning, a lot of perceptions and ideas come to mind, especially also for people in the field. There might be new data scientists, and the perception is that AI workloads evolve all around building a model. So productionizing machine learning is often thought of building a model. You see it here on the left-hand side, almost as its only task. But there's many requirements that are easily overlooked. And the reality of machine learning workloads is much more diverse, especially if you want to operationalize them and have machine learning reach your users or drive some value within your business. So instead of just the step of building a model, you have many more steps, as you see here on the right-hand side. And these tasks could evolve around the data, storage of that, retraining, monitoring, validation, either of the model output or the data. There might be elements of access, of security, of maintenance, and ethics potentially as well. So there's a lot more than just building a model, and this is where the complexity comes in, because machine learning researchers and data scientists are often concerned with the building and creation of machine learning models and putting the AI into place. And their skill sets needed for many of these other tasks are much more rooted in traditional software engineering or DevOps. So this is where the machine learning field fuses a bit with the field of DevOps and creates this new area of MLOps, machine learning operations, that really tries to take a model and put it in production. So this is one reason why it's difficult to productionize machine learning workloads. And as promised, we can illustrate this a little bit more by looking at the life cycle of a machine learning project. So when we work with clients, Datatonic, this is an approach we often take to go from ideation to implementation of a machine learning model. We start all the way on the left-hand side in the discovery phase. This is very much concerned around data analysis and identifying where the machine learning or any algorithmic design can actually help the business, for the business to draw value, whether it is not building recommendations or forecasting for financial solutions, for example. After data discovery and use case discovery, if there is indication that machine learning can help here, we would quickly want to move to a pilot stage and put this to the test. And this is where some initial models will be built, some shortcuts will be taken for an MVP to materialize, and then we can actually measure some business metrics, some KPI, and see, okay, this is successful machine learning implementation, or no, this does not work. We need to go back to the drawing board or actually not move ahead with this solution at all. But let's assume we want to deploy a solution that we find is very successful. Then we have phases 3, 4, and 5. Deployment, monitor, and optimize. And these are very much the areas where machine learning operations can help. because there's many tasks in these 3 steps where you want to bring in sound software engineering practices and are concerned about iterative model development and deployment, about the monitoring aspect of it. This could be even on the performance level of the model or the accuracy and the uptime. And lastly, you probably want to improve on the model and you want to bring in some elements of continuous iterations, retraining, and potentially also tweaking the serving nature of the model to achieve cheaper ways to reach your users with predictions or to drop down latency. So as we go through this process, we go from data gathering to assessing use cases, and then circle very tightly around the model deployment, and then lastly go into more operational modes for monitoring and optimization. So there's a lot of tasks on these slides. Don't want to go into the detail, but I just want to highlight that the area of machine learning operations really falls into the later stage of the machine learning lifecycle on the deployment, monitoring, and optimization. So to really put this into practice, we can actually conceptualize an idea on productionizing a machine learning model quite quickly and quite easily. So without over-engineering anything, if we think very much from a data scientist perspective, I have a model and I want this to be a prediction service and reached by users, let's say on-site recommendations, product recommendations, such as Netflix or Spotify do. What's the easy, the tactical way to achieve this as quickly as possible? And here I show you a diagram that we often go ahead with to really put this into place fast and effectively. And it starts at the top with some historic data. You then move into the data extraction, analysis. There's a few steps around model experimentation, and this is often very manual, driven by data scientists. The data needs to be prepared, a model needs to be trained and evaluated. How this is then moved into production is via an interface such as a model registry. So we have a trained model and we can export this, and this could be then deposited in a registry or any sort of storage. It's going to be quite simple. And this is then where the operational side can pick this up into an API or a prediction service and serve predictions at users' demand, for example. So here we kind of split the experimentation and the serving part, and it allows a data scientist to go through these manual steps, maybe only once, and the prediction service still have a model ready and available. But of course, there's a lot missing here. There's a lot missing towards monitoring and towards continuous deployment and evolution of the solution. So where we really want to go to is a much more transformational picture of machine learning deployments. And this is a bit a diagram of how we see the machine learning ops components to come together to really form a solution where you can update, monitor, and improve on machine learning use cases, even multiple ones in a single platform. Without going into too much detail, I just want to highlight a few aspects of this fairly complex diagram. There's still an element of data analysis at the top left, and that can be baked into an orchestrated experimental environment where you can try and scale the experiment in parallel. Important here now is that the model is treated as source code, as code. So improvements and changes and tweaks to the model will all be versioned into code. And this can be saved in the source repository. So we add the element of versioning, which adds traceability to your outputs and machine learning use cases. This also allows a CI process to then build the whole machine learning pipeline and its individual components. You can drop some of that in artifact storage or package it up. And it allows a continuous deployment element to be added as well. So models can be updated via code, and it can trigger a whole chain of a redeployment, including validation. Of course, there's still a trained model instance, which you see at the right-hand side, and that gets integrated again by your usual CD processes into your model service and your prediction service. The previous Steps to generate a model were very manual. Maybe a data scientist would just go through some Python notebooks one step by one. Here we want to automate this. This is the central part here. So all the steps that produce a new model, a trained materialized instance, such as data extraction, validation, model training, evaluation, etc., they will all be fused into an integrated pipeline and allow a new model instance to be picked up by the CD process and then baked into the next version of the prediction service. Once the service is running, or it should run continuously, there's obviously a heavy element of monitoring, which you see at the bottom. And this can be on the accuracy of the model, for example, and it can also be on the uptime and performance overall of the prediction service. If you see any degradation there, you can then trigger a rebuild of your automated pipeline and update your model either in an automated way, or you can trigger some manual intervention where you go back to the data analysis and maybe redesign some of your features and data components. So this is really where we want to go to, but of course that adds a lot of complexity. So I want to start simple and think back to this tactical view where we had a much more manual process of achieving operationalized machine learning model. And I want to give you a walkthrough of such a case with a customer story with the cosmetic retailer Lush. So if you're not familiar with Lush, they sell cosmetics, predominantly famous for their bath bombs, which you see on the picture here on the right-hand side. And as a retailer and brand, they're very environmentally conscious, and they actually want to heavily reduce the amount of plastic and packaging they have in stores. So what they want to do is get rid of as much plastics and packaging as they can and have basically shelves stocked with just the items and a few signs to indicate what these products are. This, of course, is great for the environment and much less wasteful, but it introduces some challenges for customers because you still want to get the information on the product. You might not have this available in store, or you take the product home and you don't have a label for it. So to get basically a virtual version of a label, they envisioned an app where you can take a picture of the product and the computer vision algorithm will do the image recognition and then pull in the information for this specific product. And you see this on this slide here. So you snap a picture on your phone or an in-store device and you know exactly what product it is, what the price is, and very importantly, the ingredients and allergens. Because these are cosmetics products, and of course you take them home, you put them on your skin, you take them in your bathtub, you need to be aware of what's inside. So this digital label is based on computer vision and a classification model. And when we started working with Lush, they already had a prototype of this available for iOS, but there were some issues with it. First, it was not available for Android, excluding a large part of the user base. And secondly, its performance was just hit and miss. So it would maybe recognize products in 50% of all cases. So when we started working with them, we wanted to now improve the model, first of all, bring it to Android, but also develop an MLOps approach where they can build new models and update their models as easily as possible. They did not have a data science team, so having a semi-automated process was very important for if they have new products, it will basically re-trigger the whole process of building the machine learning model and baking it into their apps, and this all done completely hands-off and completely serverless. So let's have a look at the machine learning model that actually drives the image classification. For those of you interested in machine learning, the model was built in Tensorflow, and it uses the MobileNet V2 architecture. And it's actually quite a challenging use case. You might think computer vision is a very often used machine learning use case, but this scenario is quite difficult. So Lush's product, they're all handmade, which means there's a lot of variance. They're all slightly different in terms of color. They're all slightly different in terms of texture. A lot of them are bath bombs, so that means they're round, they're about the same size. So this is not not comparing a dog versus a cat or a table versus a car and have a computer vision algorithm find an answer to that. This is doing classification amongst very similar objects. So what we did was a lot of image augmentation and careful data selection to really treat this use case well and to achieve the performance of classification we want. We used a pre-trained neural network based on MobileVet and trained on ImageNet and retrained some layers and also did some other tweaks to the architecture. And after some steps of hyperparameter tuning, we actually could improve the F1 score from 45% to 97. So now we got a model in place it's actually very good and it does the classification well. And if you're a Lush customer, you can use their Lush Labs app and actually test this. So this is great, we got the model, but now think back of what we actually want to do when we operationalize this. We want to basically update the software for new products and want to update the software and the model as we used with other apps. And Lush is extending their product catalog on a weekly basis. So for their team of non-data scientists, it's important to have this as smooth and easy as possible and as integrated with their normal software deployment circles as they used to. So we want continuous delivery, in other words, and we want to ship these models like software. And of course, as much automation as possible without manual interference. So to build out the machine learning pipeline, there's now a few steps to tackle. And again, if you're not very familiar with computer vision machine learning, the steps are roughly to pre-process the images and to then train the model. But we also want to monitor and track the performance. So we need to keep record of that. We want to have some automated element of retraining and evaluation of judging how good the model is. And we want some versioning and ability to trace back if something bad happens, for example, if the performance degrades, and if you want to revert. So these are some of the steps of the machine learning pipeline here. On the very high level, a pipeline can look like this. We know we have image data to train the models. This is the product data. And at the right-hand side, we want to have this classifier available in Android and iOS. To do this, we knew we're going to use Tensorflow as the machine learning framework and its portable component TF Lite, which allows you to build lightweight machine learning models into mobile applications. So we knew at some point we need to create a TF Lite model, and it also allows us to not just have the app on iOS, but also on Android. So now we have to build out these steps in between. And still at the very high level, these steps look like this. We have data preparation left and machine learning right. And I'll dive into these boxes in 1 minute. We built this complete process out on Google Cloud Platform. So we knew the initial step and where the images are hosted will be Google Cloud Storage. And you can imagine this, that for each of their product categories, there will be one folder, maybe with the product name, and the folder will have several training examples. So the model can learn from the data on what this specific product is, and then hopefully recognize it in the fully available app. So let's have a look at the data preparation. As I said, in improving the model performance, this was a key step. First, from the image upload, we actually move into a processing step, which was done in Apache Beam on Google Cloud's serverless product Dataflow, which allows you to process a lot of image data at scale, and we converted them into Tensorflow's own binary format TF records, which is a very effective representation of training data. We then split the data into training data and evaluation data, so we can judge the performance of the model while it's being built. And we use Google Cloud's AI platform also to launch Tensorflow data augmentation jobs completely serverless. So this is great. This whole architecture is already serverless and leverages some managed services that does not need any maintenance of infrastructure. The data augmentation is quite heavy here. A lot happens, and there is quite a few things we play with in terms of cropping images and playing with color saturation to really do well for this complex cosmetics classification use case here. The next part of the pipeline was the machine learning box. So here again, we use some of Google Cloud's managed products, and the first one will be again AI platform to launch the Tensorflow training job. This will now point to the storage where we have the training examples and run and execute the training job. And then we calculate some metrics to evaluate this. This will be the F1 score I showed before, or some other accuracy metrics. These metrics were collected and we stored them in BigQuery for further analysis and to actually track how good this model is. And it could be, for example, that if additional categories and images are included in training examples, that the performance degrades. We then also export the model as TF-Lite and push it back to Google Cloud Storage, where it then can be picked up by the continuous deployment process of Lush to be baked into the app. One more slide on the AI platform training jobs. This is a great tool, AI platform, to run distributed TensorFlow code, and you can run TensorFlow code that works on your laptop easily in the cloud with no change and use GPUs and TPUs. And that's a good way to really accelerate your training jobs, especially if you deal with a lot of image data. And then lastly, we use this to convert the model with quantization to TF-Lite. And we actually have a fully fledged computer vision classifier, which is only 3.5 megabytes in size. So ideal for mobile deployment where size is an issue and processing speed as well. I mentioned we want to evaluate the models, and this is fairly crudely but effectively done here by exporting it to BigQuery as basically a database with a SQL interface that scales very nicely for analytics jobs. And here you see, for example, a job where we had some triggered runs of model creation, and we then have some performance scores, and we can use this as some lightweight version. So to put it all into one picture, there's one thing now that's missing, and this is automation. If you look at the whole diagram, we discussed each of these elements now. We have the data preparation and the machine learning side down below. And what we now need to add is a process and orchestration job that would actually go through all these steps and trigger them one by one, or maybe pauses if something goes wrong. So when Lush wants to add a new product, all they have to do is add another folder to Google Cloud Storage, and this will then trigger this whole cascading steps of tasks until a final model version is produced. And for that, we use Apache Airflow and its managed service in Google Cloud Platform to define each of these steps as Python tasks that can then be executed. So this puts everything together into serverless machine learning pipeline, complete in Google Cloud. There's no infrastructure to be managed. We have the well-performing TF-Lite model exported at the end, and it's available then for Android and iOS apps. And yes, we saw at the beginning tweaking the model architecture from the prototype to something slightly more sophisticated in terms of neural networks and data augmentation. We achieved huge performance increase. And if you are interested, I recommend downloading the Lush Labs app and give this a go and play with it. So what have we really achieved if you think now back to how we want to operationalize machine learning platforms, machine learning pipelines? We've done the orchestration. We have scalable ML training jobs, and we've done some level of monitoring, data validation, and governance. But there's still improvements to be made. Yet, with just using a few of Google Cloud tools, we achieve this tactical state of machine learning operationalization, and we could productionize this whole flow without too much trouble. So that's amazing. We got this tactical solution done, and we have something that even non-data scientists can create new machine learning models without too much pain. But what's next? Remember, a few minutes ago, I drew this picture of this more aspirational goal of a full-fledged machine learning ops platform that can productionize a use case like we just saw for computer vision, but offer many more facilities around versioning, around monitoring, and around continuous deployment. So this diagram I very briefly explained, and I want to go back to it now to mention two tools that I think can really help getting to this transformational state. And not just then work with a single use case and a single workflow tailored to one particular data science project like I walked you through before, but actually can handle multiple data science use cases, if not all of them within an organization in parallel, and drive experimentation and drive productionization at the same time. So the tools I want to briefly mention now in the next few minutes are one, Kubeflow, and then two, Tensorflow Extended. Kubeflow, I'll explain in a minute, will actually be a helpful environment to stand up a lot of these tasks you see here. And TensorFlow Extended is very much concerned with this middle part of the diagram, where you have this automated machine learning pipeline that goes through data extraction to a trained model and deposits it in a model registry. So TensorFlow Extended part will be very much coupled and tied to the machine learning model you're building and everything concerning the data and the model itself. Kubeflow as a wider ecosystem will help with orchestration, with execution of these tasks, but also with CI/CD and with the monitoring and storing and handling of the data as well. So to explain this a bit more, I want to start with Kubeflow. So you might have heard of Kubeflow, or you hopefully have heard of Kubernetes. And Kubeflow is basically a machine learning ecosystem, a toolbox that sits on Kubernetes and is therefore quite portable and scalable. It comes with many, many components, and many are quite familiar to machine learning practitioners. So there is your familiar machine learning frameworks, such as PyTorch, TensorFlow, XGBoost. There is many components around serving and monitoring and tracing artifacts of machine learning. And of course, as it sits on a Kubernetes backbone, you can deploy this to your cloud provider or run it on-prem or even locally. The technologies Kubeflow leverages are also quite familiar in today's data science and machine learning world. There is, of course, Docker. Everything is a containerized task or operator, and it offers some facilities to drive experimentation and model development via Jupyter. Of course, everything is very heavily based on the Python ecosystem with all the available data science libraries. I mentioned a few before, but it goes obviously beyond just machine learning as well and has the full support of everything you do in terms of data processing and engineering on the Python side. One particular component of Kubeflow is Kubeflow Pipelines. And this is now really a orchestrator and end-to-end framework that aims to build these machine learning tasks we've seen before in the case study and put them into Kubeflow as a manageable and scalable process. So this is just one part of Kubeflow, but for us it's one of the most important ones because it really helps with this end-to-end orchestrations as we saw. So you can define all your tasks of data preparation, creating models, validating them. You have a lot of opportunity to inspect and experiment and do things such as hyperparameter tuning, while again, leveraging the scale of Kubernetes to do distributed training and tuning. And there's some facilities also to store models and share models within your team, for example. So as a component, it leverages Argo as an orchestration engine to chain up your machine learning tasks. It has a few UI elements as well, which makes it very easy for data scientists to not be too concerned about building containers and quite effectively look at your pipelines and look at the results, most importantly. But it also comes with a SDK in Python that you can define your pipelines and interact with as well. So Kubeflow is great to stand up a similar type of workflow as we've seen before, but also at the complexity of experimentation and monitoring. The other part is the much more model-centric one, whereas Kubeflow can really handle the CI/CD components as well, and is great on the performance monitoring and maintenance of a whole model. TensorFlow Extended is a framework of choice to really treat the machine learning pipeline as a first-class citizen that needs attention on each of the steps through the generation of the data to actually validation and scrutinization of your model output. So how that looks like is it's a pipeline built around steps within TensorFlow. So you limit yourself a little bit to the machine learning framework, but you can then build the pipelines with all the needed steps around the machine learning model to deliver against a specific use case. So this could be validating data before it goes into a training job. This could then be training the model at scale and monitoring the performance of distributed training jobs. This could be tuning the models and also validating the infrastructure it runs on. And lastly, there's components, also UI-driven, to evaluate model performance and maybe even do some investigation on weaknesses where a model does not perform well or biases as well. And then at the end, you can push the model to a serving service, and this could again sit within Kubeflow, or it could be TensorFlow serving as well. So what I want you to take away now from this session is that if you're looking to simply operationalize machine learning models, you can actually just build a custom machine learning pipeline, and it's not that hard. And you can build and leverage a lot of the serverless tools the cloud providers already have. I gave you some examples on Google Cloud Platform, but there's equivalent tools on all other cloud providers. So building a custom MLOps workflow is really not that hard, and you can really focus on the important tasks that's key for your use case. But on the other hand, there's great emerging tools such as Kubeflow and TFX, and also tools within these systems such as Kubeflow Pipelines to really build fully fledged MLOps platforms. And the benefit here is that you can really add all the bells and whistles to not just look at the specific use case, but to do holistically monitoring of your machine learning workflows, and to also drive a lot of data science use cases and machine learning models in parallel, which is great for large organizations. With that, I'm going to end this session now, and I will meet you all in the Q&A chat. But I want to thank you very much for your attention, and don't be afraid to reach out with questions if you have any after the session as well.